Now that we've learned the first derivative test and the second derivative test, let's apply it to a problem and see if we can identify which one we like more, or maybe there'll be different spots where different ones would be better than the other one. So I'm doing this on the top of page 331. All right, and so the first problem we have here is f of x is equal to x to the fourth power minus 4x cubed plus 2. And I'm going to use the first and second derivative test. So the first thing we're going to do, these are the things that are common to both tests, is we're going to take the first derivative of the function. Polynomials are good and easy to find the derivative of. That's 4x cubed minus 12x squared. And just for fun, I'm going to factor this. It's going to make our lives a little bit easier. Both of these terms have a common factor of 4x squared. So this is 4x squared times x minus 3. All right, so now that I've found the first derivative, I want to figure out where it's equal to 0, because those are all of my potential candidates for relative extrema. So 4x squared times x minus 3 is equal to 0. All right, so that's true when either 4x squared is equal to 0 or x minus 3 is equal to 0. 4x squared is equal to 0 when x is equal to 0, and x minus 3 is equal to 0 when x is equal to 3. All right, so here are the x coordinates of my two potential relative extrema. And why don't I over here show how we do this with the first derivative test, and over here with the second derivative test. All right, so the first derivative test, we've done this a couple times already. So I'm going to create a number line. And the two key parts on my number line are x equals 0 and x equals 3. And so I want to pick sample points, one from each of these three regions, and test to see if the first derivative is positive or negative in this zone. All right, so over here, I'll pick the middle one first, and I will pick x equals 1. So when x equals 1, f prime of 1 is equal to 4 times x squared, and I'm just going to put the signs down. 4 times 1 squared times 1 minus 3. All right, so this is negative, and so over this range, f is decreasing. Okay, over here in this zone, I'll take x equals negative 10. So f prime of negative 10, once again, 4. Negative 10 quantity squared is positive 100, and then negative 10 minus 3 is negative. Okay, so once again, positive times negative, this is decreasing. And then over here in this zone, I will take x equals positive 10 as my sample point. So f prime of 10 is equal to 4 times 10 squared times 10 minus 3. So over this zone, it's increasing. All right, so what does that say about our, our two candidates for extreme points? So at x equals 0, we're going from decreasing to decreasing. So x equals 0 is not a local extremum because it's going like this or something. It just keeps on decreasing. And x equals 3, so it's decreasing and then it's increasing. Decreasing and then it's increasing. So that is a local minimum. All right, so that's how we do it with the first derivative test. Let's test with the second derivative test. So for the second derivative test, we need to calculate the second derivative of f. So the first derivative is 4x cubed minus 12x squared. So the second derivative of x is equal to 12x squared minus 24x. And again, I'm going to factor out, this time it's 12x, and that leaves me with an x in the first term, and it leaves me with a 2 in the second term. So I am going to apply 0 and 3. I'm not picking points between the extreme points. I'm testing the candidates directly to see if the points are concave up or concave down at this point. So f prime of 0, if I put 0 in here, it's 12 times 0 times -2, which is just 0. All right, so since the second derivative is 0, that says it's not a local extremum, because it's a point of inflection. Again, kind of like this. And if we put in the second derivative at 3, we've got 12 times 3 times 3 minus 2, which is equal to 36, which is positive. So that means that this is a positive function, which means that it's concave up at this point. And so that's a local minimum. All right, so we see we got the same answers both ways, which is a relief, I suppose. But you can see how there are different strategies for identifying it. Which one's better than the other? It's hard to say. There are times when either one of them would be the correct thing to do. In this case, neither of them were terribly hard. The second derivative test would be a bad thing to do if finding the second derivative of the function was a hard thing to calculate. Okay, I wouldn't want to calculate the second derivative test if the second derivative was hard to calculate, but it was kind of easy to go through this with the first derivative and just kind of pick a couple local points and then just use my sign test. For instance, the problem we did at the top of the last page, where we had this awful thing with the quotient rule. Using the quotient rule again would just be, I don't even want to think about it. On the other hand, if the second derivative is something that's easy to take, like it is here, I think this was an example where the second derivative test wins out over the first derivative test. It's just a little bit less work. There's a little bit less drawing that you need to point things out. All right, so you'll want to be familiar with both of them because the AP exam is certainly capable of coming out with problems where maybe you've got a table and you've got second derivative values, but you only have the first derivative values for a specific number of points. So that's a case where you would need to understand the second derivative test in order to do that. On the other hand, if they gave you the first derivative over a bunch of ranges, but didn't give you the function, so you couldn't calculate the second derivative, you'd need to be familiar with the first derivative test. So have both of them close to your hearts. And as you're going through the homework, see if you can get a feel for which one of those two cases is the easier one to deal with for each of those cases.